start recording, go to the slides. So today's slides are a new topic. We finished files, which was a nice breath of fresh air in between some hard topics. I am sorry to say that the next topic is also difficult. It's probably one of the most difficult in this class. It's called recursion. So in addition to the warning signs, I've also put in a skull. So please pay extra attention. There's a lot of memes to go along with recursion because everybody it's so difficult. People like to make fun of it. So at least you'll see plenty of memes on the internet about this, and you'll be able to commiserate with all the people who share them. So let us begin. Let's talk about what recursion is all about. It's all about finding a smaller version of yourself. All these pictures are going to make sense, I promise. It's a smaller version of yourself inside of yourself. That's what you're looking for when you're solving a recursive problem. Smaller version of yourself inside of yourself, which then goes and solves a smaller version of itself inside of itself, and so on and so forth. That's turtles all the way down, right? So here's a lot of fun examples of recursion, that idea, finding something inside of itself. Here is a fractal. Here's the big fractal. There's the fractal inside of itself. There's the fractal inside of itself. There's the fractal inside of itself. And in every direction, right? They're all, just keep on zooming in, you see the same thing. Find the problem inside of itself. Same with these Russian stacking dolls. Click, click, click. Smaller doll inside of a doll, right? That's the problem we're going to be looking into. And this old, I think it's a tea tin. It has a picture of the tea tin inside of it, which then, of course, will also have a picture of a woman holding the tea tin inside of it, so on and so on, forever until the end of time. That's recursion. You find yourself inside of yourself. That's going to be the gist of today, okay? And the next time, too. So, yeah, that's where we're going. Recursion is the opposite, I would say, of this thing called iteration, which is what we've been doing so far, okay? Finding yourself inside of yourself lets you loop. It's essentially a different way of looping. Iteration, though, is the opposite of recursion. What we've been doing so far is iterating. When we have a repetitive problem in front of us, we use a loop. We use what's called an iterative solution. We're iterating through something. We're using iteration. So whenever you use a while loop or a for loop, another word for that is you're using iteration to solve the problem. You're going through something. You are repeating using a loop, okay? So when you do for int I equals 0, I is less than 42, I plus plus to solve your problem. Oops, I need an I in there somewhere. That's called iteration. This loop is iterating through something, okay? That's the idea. So, yeah, recursion is looping without using loops. And this will become more and more apparent as we have some examples, all right? But let's see, how far are we going today? That far, okay. Let's just talk about recursion and not go to code just yet, okay? Let's talk about that for a while. Let's solve a recursive problem just on paper, and then we'll code it up. That's going to be how this will work. So here's the basic idea of recursion. The standard example is calculating the factorial of a number. So that'll be our first example. So recursion, you solve a problem using recursion when you find smaller versions of that problem inside of itself. You solve a problem using smaller versions of itself, smaller versions of that same problem, okay? And you're going to end up building up a bigger answer using the smaller solution. Like you send off the smaller solution to go and find out the answer to that smaller problem, and then you do the final thing to make it the bigger solution. That'll make sense in just a second, I promise. So the standard example is factorial. Factorial is a recursive problem that can be solved. Does everybody remember what a factorial is, first of all? It's that exclamation point from math. So 5 factorial is defined to be 5 times 4 times 3 times 2 times 1. Yes, remember this? So that's a factorial, and I claim that factorial is a recursively solvable problem. You can find smaller versions of factorial inside of itself. All right, so here is my question for you. I'll give you a minute to think about it, and we'll come back. You'll tell me what to circle. But factorial, it is a recursive problem. Can you find a smaller factorial inside of 5 factorial? 5 times 4 times 3 times 2 times 1. take a minute, convince your neighbors. If they don't see it, show them what you see. Can somebody find that smaller factorial? So take a minute to try that, and I'll have you tell me what you see. Do you see the problem inside of itself? Can you find a smaller factorial inside of 5 factorial? All right, that is my very quick 1-minute timer. What did we see? Did we find a smaller factorial inside of 5 factorial? If so, where is it? Somebody tell me. Yeah, it totally works. Does everybody see it? 4 factorials right here. There's 4 factorial. Are there any questions about that? Is that the only smaller factorial? There's plenty more, right? It goes all the way down. There's 3 factorial. Here's 2 factorial. Here's 1 factorial. Technically, 0 factorial is defined to be 1 as well, so that's technically also there, if you want to do it that way. But what do you know? 5 factorial, we can break it down to 5. Usually when you're solving a problem, you're finding it inside of itself. You want the next smaller one. So 4 factorial is the next smaller one. That's the one we're usually going to care about. 5 factorial, that's equal to 5 times 4 factorial. That is a correct equation, right? Any questions about that? Does that make sense? We're finding a problem inside of itself. All right, let's extrapolate from there. So 5 factorial equals 5 times 4 factorial. This still works for the other ones, right? 5 factorial equals 5 times 4 factorial. But you can use the same logic to show that 4 factorial is also equal to 4 times 3 factorial, because 4 factorial is 4 times 3 times 2 times 1. There's 3 factorial. So it seems like this equation is always going to hold in this way. Do we see the pattern? Because our next goal is going to be to pick out this pattern. And what's 3 factorial but 3 factorial equals 3 times 2 times 1? That's 3 times 2 factorial, right? 3 times 2 factorial. What's 2 factorial but 2 times 1 factorial? Right? Does that make sense? You go on and go on and go on forever and ever and ever. So in general, like replace 5 with n. In general, n factorial is equal to, we just discovered, it's equal to, well, if 5 was n, that means n times, and then how do you get 4 from 5 if 5 is n? N minus 1 factorial. So that's the general answer. Does that make sense? N factorial is equal to n times n minus 1 factorial. Woohoo! This is called the recursive case. And it holds. It holds for 5 factorial, for 4 factorial, 3 factorial, 2 factorial. It's going to work, right? So you're using that smaller sub-problem. So that's when you find a smaller problem. It's called a sub-problem, problem inside of the problem. Here it is. Here's the sub-problem for 5 factorial. It's the same problem, just smaller. There it is. So you can build up the final answer with the solution to the subproblem. Like you give me 4 factorial, I know how to give you 5 factorial by just multiplying 5 by that answer. See that? That's going to be the way we do it. Okay? That's the idea. Using a smaller subproblem to solve the bigger problem. This recursive case, though, eventually breaks down. Watch. 2 factorial is equal to 2 times 1 factorial, that's correct. 1 factorial, that's equal to, if we keep using the recursive case, that's equal to 1 times 0 factorial, right? If we keep following our rule. This is still technically correct. 1 times 0 factorial is defined to be 1. But if we kept following the rule here at 0 factorial, we'd say, all right, 0 factorial is equal to 0 times negative 1 factorial. And this is where it stops making sense. Now we've just multiplied 0 by something, so our entire answer becomes 0, right? And then also negative 1 factorial doesn't really exist. So we don't want to go this far. Now this recursive case stops making sense. We wanted to stop before then, okay? How about we stop at 1? Just, if you give me 1 factorial, I know the answer immediately, okay? So there's always a question of when do we stop? Our recursive case keeps solving a smaller and smaller and smaller subproblem. Eventually, we get to a small enough problem where continuing this method will either break down or there's no need. Okay, so you ask the question, when does the problem get so tiny that you have the answer in front of you? You don't have to do any extra work. You don't have to solve a smaller problem. Okay? And I think what we just noticed is if you ask me for 1 factorial, I immediately know the answer. I don't have to use any more factorials. I don't have to solve this problem anymore inside of itself. If you ask me for 1 factorial, the answer is immediately 1. Does that make sense? I don't have to do my recursive case. I'm done. The answer is just 1. I don't have to do any extra work. So that could be our stopping condition. All right, and this is called a base case. So this, we discovered that 1 factorial, if we were to stop right here, this would be a nice stopping place. Go any further, it gets a little weird. So that's called a base case. It's that stopping condition for your recursive problem. So we noticed that if you ask me for 1 factorial, I can just immediately give you back 1 as the answer. I don't have to do any more inner factorials, all right? And so a recursive solution is always a combination of a recursive case that solves the general problem and usually works out, and then a base case for when that general problem keeps going smaller and smaller and smaller. We eventually need that to stop, right? We need to stop our looping. So you need those two together, and that gives you the solution to the problem. Are there any questions about anything I said on this slide? Because this is going to be the way we think for this chapter, for this topic. We find a problem inside of itself. We generalize, given some examples, we generalize that to a recursive case, and then we notice that there are some times when does the problem get so small that we're done immediately. We don't have to go any further. All right, base case and recursive case. So those two solutions together give us a way to solve for a factorial. The base case, you ask for 1 factorial. I know the answer is immediately 1. I'll tell you that. Recursive case, you ask me for any other n factorial. I know that the answer is equal to n times n minus 1 factorial. We figured that out. Okay? And so here's how you could solve for 5 factorial using these ideas. How you can actually compute 5 factorial. All right, so 5 factorial using the recursive case, well, all right, that's going to be 5 times 4 factorial. All right, now I have to go off and compute 4 factorial. So what's 4 factorial using this rule again? It's not 1 yet. I can't use this one yet. 4 factorial, that's 4 times 3 factorial, right? What's 3 factorial? I need to go and compute that before I multiply it by 4. 3 factorial is 3 times 2 factorial. What's 2 factorial? That's 2 times 1 factorial. Let me draw my ones like that. What's 1 factorial? Ooh, that's my base case. I can stop right there. My answer is 1 for 1 factorial, and now I can tell whoever asked me about 1 factorial my answer. My answer is 1. Okay? And then this line, which was waiting for 1 factorial solution, it just got it. It can multiply its 2 by that answer, which was 1, so it can give back 2 as the answer for 2 factorial. And it can wind itself back up and give back the final answer. So this was waiting on 2 factorial. We just computed it. It was 2. It can multiply 3 by that to get 3 factorial. 3 factorial ends up being 6. We go off and we tell it, whoever asked us for it. All right. This was waiting on 3 factorial. We just got back 6 as the answer. We can multiply our 4 by that and give back 24, right, as the answer for 4 factorial. And this was waiting on 4 factorial to multiply by its 5. And oh man, did we just get back an answer for 4 factorial? We can give back the answer for 5 factorial by multiplying that 5 in. And so the answer is 120, and that is how recursion works. You go down to your base case, and then you work your way back up and build up the answer. And you get back the correct solution. 5 factorial really is 120. What questions do we have about this? This is definitely a new way of thinking. The examples are only going to get more difficult, so please ask questions now. Alrighty then. So notice that some of these, like there are some cases where this doesn't work at all. Like if you ask for -1 factorial, you're not going to hit this rule. You're going to try and match against this rule, and it's just going to go on forever and ever and ever until the end of time. You kind of want to make sure that never happens, so that's a little side case that you might have to have an if statement for or something. But in general, if you give me a positive number, I can correctly find you the factorial with these rules. All right, so let us compute this. Let's write code that works like this, that solves a problem in this way. That is our goal now. How can we write code that does this? Because this is computer science class. So, all right. Usually when we're writing programs, we solve a problem by either like writing a class with a bunch of methods, or we're just trying to compute an answer for a single question, right? Give me the factorial of this. We'll just write a function for that. So in C++, we usually solve a problem by writing a function. If we would like to solve a problem recursively, we're asking inside of the factorial function for a smaller factorial. But wait, we're the ones who are computing factorial. So that means a recursive function, a function that solves a problem recursively, must call itself. Ooh, we've never done that before. And you have to call yourself on a smaller version of that same problem. Otherwise, you're never going to get to the base case. Okay? Crazy. So you have your int, we'll call it fact or something. Give me the factorial of a number n, and you have your body. Inside of that body, you are going to be calling fact of n minus 1. Compute the one smaller factorial. Does that make sense? That's your recursive case. Like, what is your recursive case? It's, all right, I need to give back n times me minus 1 factorial. So you're going to call yourself, return n times fact of n minus 1. And this is inside of the fact function definition. All right? If you're in the base case, you know that the answer is immediately 1 if somebody's trying to ask for the factorial of 1. But that is the answer. That's the way it works. And then I'll show you the same thing doing loops, but we'll get the same answer. It's a function that calls itself. That's the key. That's what recursion is all about. We're working on ourselves. So let's code this up. Let's make it happen. So factorial.cpp. Factorial.cpp. Let's code up the factorial problem, and let's ask for, of course, fact of 5. So we need to make the fact function now. Int fact takes a number n, and it's supposed to return n factorial. Okay, that's where we're going with this. And so, all right, we need to figure out which of these rules applies to the n that we are asked to give the factorial of. So let's figure out first if we're in the base case or the recursive case. Because if n is 1, right, if n is equal to 1, we're being asked for the factorial of 1. We immediately know the answer. The answer is just 1. So give back 1 in that case. Otherwise, this was the base case. 1 factorial is equal to just 1. Otherwise, we're in the recursive case. Recursive case, n factorial is equal to n times n minus 1 factorial. All right, we need to give that back. That's just return n times n minus 1 factorial. Well, that's us. fact of n minus 1. Return something involving ourselves. Crazy. And that's this. I also pasted it here. Return n times fact of n minus 1. It really is going to work like this. And this is going to solve our problem. This is going to compute n factorial for any n, including 5. So we should see 120 printed out. G++ factorial dash O factorial. 120. It did it. It solved the problem. There are no loops anywhere. It was the recursion that did the looping for us. Oops. Didn't want to go there. It's essentially computing in this kind of way, the way that I was explaining here. And I'll draw that in just a second in a different way. But are there any questions about what I just did? That's a recursive function. We came up with those two rules, the recursive case and the base case. We translated them to code. It involved our function that we're implementing calling itself. And it is somehow magically computing the right answer. All right. Now we can totally do this iteratively. This was recursively. You can use loops and do the same thing. You can just iterate. I don't know. I guess we have time for that. Why not? So fact iterative. The other way to do this would be, oh gosh, there. Fact iterative. This would be using loops, right? So if you'd have to build up a product, and product started at 1, and then multiply all the numbers from int I equals n all the way down to 1, I minus minus, product equals product times I. That would multiply all the numbers from n to 1 into this product variable and return product. What have I done wrong? Huh? Oh, sorry, not while 4. 4 into I equals n. If only we could do it that way. So that's fact iterative. That would also work. That's the way we might know how. Boop. They both give back 120. And so there's some reason why these are equivalent. These functions are essentially doing the same thing somehow. And that's what I want to explain to you for the rest of these slides. So now we have two options, right? We have two options to implementing the factorial function and any other function that uses loops, right? It can always be translated into a recursive solution. We have options now. Sometimes it's infinitely easier to think about a problem in terms of recursion. I promise. One day, recursion is going to be very, very helpful. If not tomorrow, definitely in CSCI 41. All right? So let me explain why this function works, why it's giving back 120 again in a different way. Let's use a stack diagram, all right? Because it's very cool how it's building up its answer. It's looping using the stack. And we'll see that in just a second. So yeah, the runtime stack looks very interesting for recursive functions. So in main, we called fact of 120, or sorry, fact of 5. So in main, we called fact of 5, and so this is what the stack looks like on the first call. We ask for fact of 5, essentially. I'll draw it like this. And then, fact of 5, it's got to figure out, all right, which side am I on? Is 5 equal to 1? No. So we hit the recursive case. We need to multiply our 5, our n, by fact of 4. That's n minus 1. So we have to go off and compute this answer because we don't know it yet. And we have to wait on that answer so that we can, and then once we get it back, we can multiply our n into that and return finally. So this recursive case, it needs to go off and compute fact of 4 first so that it can multiply 5 by that and then return. So it's not ready to return yet. It's got to go off and compute first fact of 4 because it doesn't know that yet. So it goes off, computes fact of 4. So now I have 2 calls to fact on the stack. Neither have completed. Fact of 5 calls fact of 4. Again, we're in the recursive case where n is 4 now. We ask for, we're going to multiply 4 by fact of 3. We need to go off and compute fact of 3. So it's going to call itself first. Get back that answer. Fact of 3. All right. That's the idea. And really, I draw it like this, but really it's a variable called n. It's set to 5. It's a variable called n. It's set to 4. That's what's really going on here. They're all different n's, though. This n is set to 3. It's a bunch of different versions of the same function being called all at once. All right. Fact of 3, again, hits the recursive case. It needs to go off and compute fact of 2 before it can return its answer. Fact of 3 goes off and asks for fact of 2. So again, it has its n parameter as a variable. It's a local variable stored as 2. And then fact of 1 gets called from fact of 2 because it's still the recursive case. It needs to multiply its 2 by fact of 1, whatever that is. It needs to go off and compute it first, get back that answer. Fact of 1, and it has its little n variable parameter set to 1. And now we're in the base case. We have 5 calls to fact on the stack right now. None of them have completed. They're all waiting on each other. They were all waiting right here so they can multiply their n by the answer that they got back. All right? That's what's going on. And fact of 1 is finally the base case. If n is 1, return 1. It's like, okay, I have my answer. Here you go. It can return back 1 to whoever was calling it. And now it pops itself off the stack. And I'll just keep it here with a slash, but know that we're back in fact of 2 now. It just got back the answer from fact of 1. Oh man, I can multiply my 2 by that answer. I can give back my final answer. It's 1 times 2. 2. That's the result for factorial of 2. Now it's done. Back to whoever called it. Do we see how it's unwinding? Are there any questions about that? That's the key. Then fact of 3 was sitting here waiting on fact of 2. It can finally multiply its 3 by fact of 2's answer. 3 times 2 is 6. It gives back 6. Now it's done with its work. Returns. Now we're back in fact of 4, who was waiting on fact of 3. We finally got back that answer. We can multiply our 4 by that. 4 times 6 and give back that answer. 4 times 6 is 24. Now fact of 4 has finished its work. Now we're back in the original call to fact, who was waiting so patiently on fact of 4 to complete, so that it could multiply its 5 by fact of 4. Fact of 4 took a long time to compute its answer. It finally got it, though. We have an answer for fact of 4. We'll multiply our 5 by that and give it back to whoever called us. So 5 times 24, that's 120. Fact of 5 has finished. That's its answer. And now main finally prints out that answer, because that's what we're doing with the C outline. Boop. Main's the one who asked for fact of 5 in the first place, so that it could print out whatever it got back from fact of 5. And then finally 120 appears on our terminal screen. So you build up your computation. Everybody's waiting on everybody else. And then once you hit the base case, you start unwinding. Everybody starts giving back answers to the people who are asking for those answers. That is recursion. Are there any questions about that? That's definitely one of those things that's going to take a while to sink in. I was not a master of recursion by the end of my CSCI 40 class. I was barely a master of recursion by the time I finished a 4-year college degree. This is the way it works, though. Are we good to keep going? All right, it's a little weird, but I promise it will make sense with enough examples. That's how it is computing its answer. It's looping, just in a very weird way. Let me prove to you, this is going to make even less sense, maybe, unless you're like a math major. Let me prove to you why recursion works, because it's important to at least have a general vague idea of why it's doing the right thing, because that will help when you're solving your problems. Because there is a magic thing in recursion. You get to assume something, and that makes the solution just pop out of thin air. And it's so cool once you get the hang of it. All right? So here's why recursion does the right thing. Well, let's pretend that our problem is very general. It's a problem P, like it's the factorial problem. It's P, though. We'll call it P because several problems can be recursive. To solve a problem recursively, you have to give 2 things. You have to give the base case, saying, I know how to solve the smallest version of the problem. So maybe that's the solution for P of 0. Like, I know that answer. I know how to give you back the answer if you ask for P of 0. I know that answer. I have that immediately. And then also the recursive case. You have to give this. What is the recursive case, though? This is maybe a philosophical question. But if you scroll back up and you think about it long enough, the recursive case is saying, if you gave me the answer to a one smaller version of the problem, I can solve the original problem. That's essentially how you would frame the recursive case. You give me the answer to one smaller problem, I can build you the answer to the next bigger problem. It's a bit backwards. But we can write it like this. You give me the answer to P of k, and I know how to build you the answer to P of k plus 1. Okay, that's what the recursive case is saying. And if you take both of these together with a mathematical concept called induction, you can prove that this is always going to solve the problem for any n, P of n, for any n greater than or equal to 0. All right? And let me show you why. This, you asked for P of 5. I can build you P of 5 or P of infinity very easily, because I can start with my answer to P of 0, which I assume I have, and then I can run this rule on it forever. Just set k equal to 0 right now. Because I have P of 0, I can get P of 1 based on that recursive rule. Does that make sense? I'm just plugging in k for 0. And that'll plop out P of 1. It's like, you give me one smaller problem, I can give you the next bigger one. Well, I have one problem. Let's build up P of 1 using this rule, set k to 0. And now I have P of 1. I have that answer. So I can run this rule all over again. Set k to 1. Run this rule. I know how to get P of 2 based on this idea. Again, now I have P of 2 at my fingertips. I can use that rule to get P of 3. Now that I have P of 2, I can always get the next bigger thing once I have a smaller answer. And then you can run that forever until the end of time for any n. Does that make enough sense? When you actually program this, though, you're going to start from the original problem. Like, you're going to start from P of 5. You're going to work your way down to the base case. And then it's going to start building itself back up using this idea. That's what we were noticing happening here on the stack. That's why recursion works, in a nutshell. Are there any questions about the first half of this slide? Does that make any sense at all? It's a very, very powerful concept. And it is a bit magical. You don't actually have to go down to like the very bottom like we were doing here. You can actually do this. And this is definitely going to take a while to sink in, but it's so, so cool once it does. This is like the magical piece of recursion. You get to assume that when you make a recursive call on a smaller subproblem, you get to assume that it gives you back the right answer. You don't even have to think, hey, is that going to work? Just assume that it's going to give you back the right answer, and it will. It will, as long as you build up the larger answer correctly. It is mathematically perfectly sound for this to be true. And the reason why is because it will hit the base case and start building itself up using your correct builder-upper rule. And that is how I want you to think. So you don't even have to worry. Just assume, all right, this gives me back n minus 1 factorial. I don't know if it's going to. I get to assume that it will. How do I build up the original n factorial? Well, just multiply that by n. That's how I build up the final answer. And that is perfectly correct. That's actually how you make a mathematical proof that this really does give you back the factorial. You just get to assume that this gives you factorial of n minus 1. It will work. It's like wishful thinking that ends up being true. All right? That will take a few more examples, I think, though. But I just wanted to tell you it now because you will see this idea for the rest of your computer science career. It's very powerful. Any questions about this? I have a much more concrete question for you next. But are we good with this? Are we good with the vagueness for now? All right, here's my question for you. Power computation. Taking a number to a power, like 2.5 to the 5th power. That is a recursive problem as well. Can you find the smaller power computation inside of like 2.5 to the 5th? So write it down, expand it. 2.5 to the 5th power or something is equal to what? Can you find a smaller power computation? Something to something's power inside of this? Take a few minutes to see if you can find it and help your neighbors. I probably shouldn't say the word the. Can you find a smaller power computation? So it can be multiple. All right. I heard some of us even thinking about like how to actually generalize this, and that's great. But there are plenty of ways to break this down, right? So where this is equal to 2.5 times 2.5 times 2.5 times 2.5 times 2.5, right? What is a smaller power computation? What do we find? Yeah, 2.5 to the fourth. Yeah. And that could be anywhere. Draw your parentheses however you want. It's there somewhere. Here's 2.5 to the fourth. Usually you're looking for the next smaller one. So it's good to look for to the fourth power if you're from the fifth power. So there's 2.5 to the fourth. But still, again, you can see that like it keeps going. There's 2.5 to the third, to the second, to the first. Interesting. So that might help us inform our base case. But now we try it with an example. That's usually the first step. Let's generalize this and solve the general problem of calculating something to the other power recursively. Let's do it. Boop, boop, boop. So you did that. You found the smaller power computation inside of the power computation. But we're going to be writing a function. So we can't like write superscripts or anything. It's going to be, we're going to call it pow. Pow of xy is supposed to compute x to the yth power, right? And so we noticed that, all right, let's just use 2 this time. 2 to the fourth is equal to 2 4 times, right? And there's 2 to the third right here, 2 cubed. What's 2 cubed but 2 times 2 times 2? There's a 2 squared inside of that. And so if we keep generalizing, what's 2 squared? 2 squared is equal to 2 times 2 to the first, etc. We'll get there in a second. But just with these, you can start generalizing to a recursive case, right? Recursive case. Boop, boop. You give me, you're asking me for m to the nth power. That's equal to, just replace like the 2's and the 4's with m and n. That's equal to, well, a 2 times a 1 smaller power computation. So the original thing, that's the m in my example, the m times a 1 smaller power computation. So m times 2 to the fourth is 2 times 2 cubed. M to the n is m times m to the n minus 1. Do we see that? That's important. Boop. Just like that. That's our recursive case. And now we need to come up with a base case to stop our power computation. Base case. So we need to keep on trying this, let it get smaller and smaller. So running this recursive rule on 2 squared, that's equal to 2 times 2 to the first. That's still good. Makes sense to me. 2 to the first, that's equal to, well, you could just stop there and give back 2, but you can go further than that. Right? That's equal to 2 times 2 to the 0 using our recursive rule. And 2 to the 0 does make sense. Anything to the 0th power is correct, right? Is 1. That's fine. If you go any further than that, though, 2 to the 0 is equal to 2 times 2 to the minus 1. Okay, 2 to the minus 1 is equal to 2 times 2 to the minus 2. This is kind of like not helpful anymore. It's like 1/2. Why do we care? And this is just 1 all over again. So I think 2 to the 0 is a good place to stop. You just keep on unwinding your recursive case until it stops making sense. And I think this is a good base case. Anything to the 0th power is just immediately 1. We don't have to do any extra power computation, right? That's a perfect base case. You ask me for anything to the 0th power, it could be 1. But if you didn't want to go that far, there are options. They're just not as general. Anything to the 1st power is that thing, right? That could be another base case. That is equally valid. It just won't work for anything to the 0th power now. But we would like the most general answer. So let's make it m to the 0. Just immediately give back 1. You're asking me for the 0th power of something. Okay? I don't know why that looks weird to me, but I'll draw the 0 closer to the m. There. So yeah, the recursive case, it finds the smaller power computation to go through and build up the final answer with. And then the base case stops that power computation. Eventually we get so small we immediately know the answer to our power computation question. Does that make sense? Any questions about this analysis, how we came up with the recursive case, the base case, any of that? Because now we go and code this again, and it will work. Dun, dun, dun. So let's do pow.cpp, I guess. Oops. Don't know what happened there. But it seems to be. Why so unhappy? Oh, number sign. Alright, so let's remove all this. It's no longer called fact, it's going to be called pow. So it's pow. And you might have noticed that we can only handle integer exponents. But we can take any arbitrary thing that we're taking the exponent to. So it's double m int n, and it gives back a double. So it returns m to the nth power. That should do it. And then let's do the original one. See out pow of 2.5 to the 5th. 2 to the 4th. Those are my 2 examples, I think. So let's code this up. The main step at the beginning is always an if statement, like am I in the recursive case or am I in the base case? All right. If n is equal to 0, I'm trying to take something to the 0th power, so I just give back 1. Anything to the 0th power is 1. Base case, anything to the 0th power is 1, so I can just return 1, or 1.0 if I wanted to be pedantic about, okay, it is returning a double. Doesn't really matter though. Otherwise, I'm in the recursive case. Recursive case. M to the nth power is equal to m times m, I don't want to do this, m to the n minus 1th power. There. And so that's what I'll return now. That's equal to m times return m times m to the n minus 1th power, but we are the ones writing the power function. So it's pow m n minus 1. So it's getting smaller. It's eventually going to hit the base case and unwind the recursion. But we just get to assume this call works. It gives us back correctly m to the n minus 1th power. Using math, I know that the final answer is just 1 more m associated with that. That will give me the final answer correctly for the bigger problem. That will solve the whole thing. So we get 16 for 2 to the 4th. That makes sense. 2, 4, 8, 16. And then 2.5 to the 5th is apparently 97.6562, which we can check in Python. Oops, Python. 2.5 to the 5th. Yay. 97.6525, I guess. is their answer. Oh no, what have I just done? Interesting. I think I ended it. I didn't know you could do that. That's so cool. All right. Is it really not working? Yeah, it is there. How do I find it again? All right. Respawn? No. Unzoom. There it goes. Okay, that was a weird thing that I just discovered I could do. But it works. Are there any questions about this code? It's doing the thing. Yes, question over there. No, we're making our own version of POW, and that's the one that's taking precedence. It's shadowing the other one. Yeah, we're calling ourself. We're calling the function that we are writing inside of itself with a smaller input. I do have a diagram that I'm about to draw that might be very helpful, just like I did for Factorial. Any other questions before I give you that diagram? So let's make a bigger one. Instead of 2 to the 4th, let's do 2 to the 5th. I think that's what I have planned. And that is going to be 32. That's that answer. 2 to the 5th is 32. Let's discover how this is doing its thing. Why in the world is this working? And so I'll be flipping back and forth from here to here. But here is what happens on the stack when I call POW of 2 and 5 to ask for 2 to the 5th power. So main calls POW of 2 to the 5. Here's that call. POW, I'll just draw it like this. POW 2, 5. And now we plop ourselves here. We look, all right, what do we see? Do we see a exponent of 0? Is 5 0? No, it's not. So we are in the recursive case. We're going to return m times POW of m and n minus 1. We don't have a final answer for this yet. We have to do some multiplication. We have to actually go and call this function to get the answer first. So this is our first piece of work. We have to call ourselves recursively so we can then, once we get the answer back, multiply by our m, and then we have something to return. Does that idea make sense? That idea of waiting for this computation to finish. It's just a function call, but it's going to us. We are calling ourselves. So POW of 2 of 5, it's got to go and call POW of 2, 4 first. Then it could multiply itself by another 2. Sorry, POW 2, 4. And similarly, POW of 2, 4 is going to go and call POW of 2, 3, because it needs to multiply its 2 by POW 2 to the 3rd power, n minus 1, and then it can return something. It's not yet ready to return something, so all of these things are waiting on the stack to build up their answer. POW of 2, 3 is going to call POW of 2, 2. I think you get the idea now. POW of 2, 2 is going to call POW of 2, 1. And then POW of 2, 1 is going to ask for 2 times POW of 2 and 0, so 2 to the 0th power. Then it can give back its answer. And so here's like, and draw it like this, but really the stack, they hold their variables. The m is 2, the n is 1 here. The m is 2, the n is 0 here. So we notice we're finally in the base case. We return 1. 2 to the 0, the answer is 1. And we give that back to whoever was waiting for us. We give back our 1.0, right? Back to POW 2, 1, who was waiting right here on POW of 2, 0 to multiply its 2 and give back an answer. So now, this one's done, we're back in POW 2, 1, multiplies its 2 by the answer that we got back, and the answer is now 2. That was 2 to the 1st power, correctly given back as 2. And now we're back in POW of 2, 2, who is waiting on POW of 2, 1 to multiply its 2 and return back that answer. So it'll multiply 2 by the answer that it got back, give it back, 4. Are there any questions about how the stack is unwinding right now? That's very important. Is this making enough sense? So POW of 2, 3 now, just gotten back an answer for POW of 2, 2. It was waiting on that. It can multiply its 2 by that and give back its final answer. 2 times 4 is 8. Now POW of 2, 3 is done. It's correctly computed 2 to the 3rd power. Now we go back to 2 to the 4th, who was waiting for 2 to the 3rd to complete, because its n was 4, n was 2 again. It can multiply its 2 by that answer and give back something to whoever was asking it for the answer. So it's ready to give back 16 to whoever called it. And now finally we're in the original call to POW that we were really wanting to know the answer for. POW of 2.5 called POW of 2.4. It was waiting on that answer so that it could multiply its 2 by that and give back its final answer, which is 32. Back to main. You can then go and print it. That's what it was waiting on. Does that help? Does that make anything more clear? Does that answer your question? Any questions coming up based on that? So definitely study these diagrams. This is going to help you get a grip on what recursion is doing. Are we still okay? I have a fun term to teach you next. So, yeah. If we're still okay, definitely come back and study this. I promise it will make sense if it's not right now. I want to teach you what a Stack Overflow is, because I'm sure you've been on this website a bunch of times in this class. I want to teach you why it's called Stack Overflow. What in the world is that? It has to do with recursion. So, just like you can mess up an iterative solution, you can end up with an infinite loop, right? And then it'll just never stop. You got to kill it with Control-C. You can have an infinite loop with recursion. Totally possible. That's called a stack overflow. It's actually a runtime error when you have an infinite loop with recursion, because every time you call yourself, it takes memory. You have to remember the parameters that you're calling your smaller function with, and that takes memory. So if you call yourself forever accidentally, you're going to keep allocating more and more memory for those parameters, and eventually you're going to run out. And that blows up your stack, and you get what's called a stack overflow. It really shows up as a seg fault, though, because you run out of memory. No more memory to call a function with. So a stack overflow is when your stack gets so big that you run out of memory, just for the reasons that I was saying. So every stack frame takes up memory. It needs to store the parameters, the local variables, who it needs to return to. All that stuff gets stored on the stack. And so every time you call yourself, that takes up some space. So yeah, let me show you some examples of stack overflows, and then you will have a better appreciation of that website, stackoverflow.cpp. So I don't know, let's go back to fact. Let's steal this code. And I'll copy fact twice. Here's fact with the first problem. It'll be called fact 1. And then I'll make fact 2 as well. They both will be incorrect versions of Factorial, though. Here's fact 2 this time. All right. Right now they're both correct, but let's mess something up. So the easiest way to have a stack overflow is to forget your base case, because then your program's never going to stop. It's like, what's the factorial of, let's get rid of this. What's the factorial of 3? Well, it's 3 times the factorial of 2. What's the factorial of 2? Well, it's 2 times the factorial of 1. What's the factorial of 1? It's 1 times the factorial of 0. What's the factorial of 0? Well, it's 0 times the factorial of negative 1. Factorial of negative 2. Factorial of negative 3. Keep on going forever and ever and ever until the end of time, because there's no stopping condition, right? So this is an infinite loop. I hope you see it. Forget the base case. So this one, issue 1, forgets the base case. So it'll keep on calling itself forever. What's the factorial of negative 3? Well, it's negative 3 times the factorial of negative 4. It'll just keep on going past 0, and it will never work out. So this is fact 1. That's that for fact 1 of 5. It'll just never stop. So whee! And so I get a seg fault, because I run out of memory. It tried to call itself way too many times. And if that's not clear, like here, I can print out inside fact 1 of, and then I'll print out n. So every time I call fact 1 recursively, I'll be printing this out as well. Oops. Whee! So it's calling itself forever and ever and ever. It's getting smaller and smaller. You have enough memory in your computer for this to go for a while, And eventually it's going to crash, though. It's going to run out of space. There it is. Apparently my computer has enough memory to handle a few 100,000 calls to fact inside of fact. Isn't that fun? So that's the first error. That's a stack overflow. Program never stops. The next easiest way to have a stack overflow, the next easiest way to get recursion wrong is to remember your base case, but forget to make a smaller recursive call, right? You have to make progress towards your base case, otherwise you will never stop and get to it. So it is correct in math to say n factorial is equal to n factorial, but it is not correct to say that in C++, because you're never going to get to a smaller subproblem. So this is a correct base case. This is an incorrect recursive case. Let me change it to be incorrect. What's fact 2 of n? Well, it's just fact 2 of n. So it like throws off the same problem to itself again. It'll just keep calling itself with fact 2 of n forever and ever and ever until the end of time. So cout. Inside fact 2 of n this time. And it'll print out what it's doing, where it is. I have to comment out this first call because otherwise it'll never get to it, right? So let's call fact 2 of 5 this time. So what's fact 2 of 5? Oh, it's fact 2 of 5. So it calls itself forever and ever and ever, a few 100,000 times all over again, and eventually it'll crash with a seg fault, which means it had no more memory to call itself one more time. Okay? So that is another example of a stack overflow. Any questions about this? So those are the two most common ways to get recursion wrong. So remember your base case, and also remember to make progress. This was issue 2. Recursive call does not make progress towards the base case. You always have to call yourself with a smaller input. Build up the answer. Are we good with that? All right. Yeah, for my last and final trick of the day before I show you your next lab, let me teach you the Fibonacci function, or about the Fibonacci sequence first, and then there's a function that's recursive that computes the nth element of the Fibonacci sequence. All right? So it's called, I'll just call the function fib, I think. But here's the idea. This is fun to look up if you've never heard of the word Fibonacci before. Maybe we have. But Fibonacci sequence, if you look that up, go to Wikipedia, it's just this very cool mathematical quirk, like it's found all over nature. The Fibonacci numbers approximate some universal constant called the golden ratio, or phi. It's just beautiful. There's a lot of like shell-like patterns. There's a lot of fractals. But the Fibonacci numbers, it's just a sequence of numbers. They start with these two numbers, and then the next element of the sequence is in terms of the previous two. All right? So, yeah. The Fibonacci sequence, it's a mathematical sequence. It starts with 0 and 1, and then it goes 1, 2, 3, 5, 8, 13, 21. And the next element in the sequence, after you have the first two, of course, is the sum of the two previous elements. So 0, it goes 0 and then 1. And then to make the next element of the sequence, you add together the previous two. So you take those two and you add them together and you make 1. Does that make sense? That's how you build up the next one. So these two together, you add them, and we make 1 as the next element. I guess I can draw both ones like this. And now, if I'm trying to ask for this element, how do I figure out what it is? Well, I add the two previous elements here. Boop, boop, add those together to make 2. Then if I want this next element, I add the two previous elements again to make 3. Bring them in together to make 3. And then it goes 5. 5 plus 3 is 8. 8 plus 5 is 13. Dot, dot, dot. And so all these numbers, the ratio between the two previous ones, they approximate a nice golden ratio of phi. And you can ask for, like, what's the 0th Fibonacci number? That's 0. That's the 0th Fibonacci number. This is the first Fibonacci number. Fibonacci number 2, Fibonacci number 3, Fibonacci number 4, 5, 6, 7. So there's a sequence, right? There's an order to the sequence. And it's a recursive order. We would like to write a function called fib of n to calculate the nth Fibonacci number, to give back. Like, if you ask for 4, it gives you back 3. If you ask for 7, it gives you back 13. Calculate the 7th Fibonacci number, please. Okay? And this is a recursive problem, because look at how beautiful and easily this falls out. Recursive case. If you ask me for fib of n, the nth Fibonacci number, well, what is fib of 7 but fib of 6 plus fib of 5? Generalizing that, fib of n is equal to fib of n minus 1 plus fib of n minus 2. Does that make sense? That's the recursive case. Just the 2 previous elements of the sequence makes the next one. That just falls out immediately. It's very beautiful. You do though need 2 base cases for once, because if you are trying to ask for the 0th Fibonacci number, there are no 2 previous elements, right? There's nothing to use there. You have to like hard code that the answer is 0. Same for this 1. If you ask for the Fibonacci number 1, again, there are not 2 previous elements. There's 1 previous element, but not 2, so I can't add them together. So the recursive case would again not work. And so I need 2 base cases to get it all started. You ask me for the 0th Fibonacci number, the answer is 0. You ask me for the 1th Fibonacci number, the answer is 1. Okay, so that's why you need 2 base cases, because then after that, there are always 2 previous elements that you can ask for. Any questions about that? So you need 2 base cases, and in the recursive case, you're going to return this plus this. You're actually going to make 2 recursive calls. Isn't that cool? So let me code up that for you, and yeah, you could do this with a loop, or you could do it with recursion. It's kind of beautiful when it's recursive, but it is very inefficient. So we'll talk about that next time. So let's make cout, I don't know, fib of 7. Let's ask for that number 13 here. So the 7th Fibonacci number is the number 13, and let's implement the recursive case and the base cases. So int fib, int n, this supposed to return the nth Fibonacci number. And again, you always check, am I in the recursive case or am I in a base case? So our 2 base cases are, you're asking for fib of 0 or fib of 1. If n is 0, then the result is immediately 0. If n is 1, the result is immediately 1. Otherwise, you're in the recursive case. All right? Else recursive case, you return, well, what is the nth Fibonacci number but the sum of the 2 previous ones? Fib of n is equal to fib of n minus 1 plus fib of n minus 2. Yay. And so this will calculate the 7th element of that sequence. And we get 13. Yay. Any questions about this? Do you see how I created the recursive case and the base cases? Does it make sense how this implementation matches those? So there's a very interesting issue with the Fibonacci implementation this way. The recursive implementation of Fibonacci in this particular way is kind of horrible. Because if I ask for fib of 100, watch. Boop, boop. Surely it will finish soon. It actually will take longer than the universe has existed for this to finish. So there's an issue there that we'll talk about next time. But it doesn't mean it's not a beautiful implementation. So that is Fibonacci. It's a bit more efficient to do it with just a loop, though. But there is a reason you're learning about recursion, I promise. Any questions about any of the stuff we talked about today before I show you your next lab? All right. So Lab 7, this will be due after the midterm, week 13. Let's talk about it. So this one's about pointers. Ooh. So this is lab 7. Let's go look at the starter code. Let's make this window large. A double purpose of this lab is to teach you what's really going on under the hood in C++ when you use classes. Like, how in the world is a class implemented? Why are methods working the way they do? So this will also help with that. Lab was it 07? Yeah. So here are all the files, all of these bad boys right there, and here they are again. There's two kind of parts, two major parts. The first one is just use pointers to do something interesting. So the first one is called the rotate3 function, and here's what it's supposed to do. So you're going to implement the rotate3 function. There's a header file and a C++ file. So here's the header file. Rotate3 takes 3 int pointers, and it swaps the values. It swaps the integers that they're pointing to. Okay? That's what needs to happen. You're going to rotate those 3 integers to the right, essentially. And so here's where you implement it in the rotate3 .cpp file. And so you are given a pointer to 3 numbers. So say somebody called rotate3 with the address of x, the address of y, and the address of z, where these are x, y, and z. What your function should do is rotate the values to the right. So what was, so like the x, now it's moving to the y. So 1, 2, 3 becomes 3, 1, 2. Does that make sense? Everything's rotating to the right. So now y is the 1, z is the 2, and then it wraps back around. So the old value of z goes around to x, rotates to the right, and it becomes 3. So that's the final memory state that should happen after you call rotate3 on pointers to those ints. Does that make sense? So you're rotating things to the right. So for example, if you had these 3 ints and you called rotate3 on x, y, and z, then y should be set to 42, z should be set to 43, and x should be set to 44. So like everybody's moving to the right. Any questions about that one? That's just using pointers to do swap-like things, but this is like a triple swap instead of a double swap, I would say. So that's the first problem for you. The next problem is definitely the fancier one. I would like you to create a fake version of a class using pointers and just functions. So we're going to make a counter class, just like I've shown you a lot before. Here's counter.h, and we're going to make our own. We're going to roll our own version of classes with structs and pointers and functions. Okay? So when you have a member function in C++, secretly, it's getting called with a pointer to the object itself. A pointer to an object gets implicitly passed in as a variable called this. Maybe you've heard about the this keyword in your book. All right? We are going to be essentially modeling that idea, but explicitly using functions. So instead of this, since that's a keyword, we can't like make a variable called int in C++. We can't make a variable called this in C++ either. We will use the word self instead. That's what Python uses anyway. So yeah, every method in our counter class, these are all in quotes, will have a first parameter for the object. More quotes. Okay? So here's what it means to be a counter object. You have a count inside of you, and if this is a class, every time like you make a counter object, you have to construct it. There's an inc method, there's a reset method, there's a get count method, but secretly in all of those methods, they took implicitly a pointer to the object you're trying to act on. And so now we're making that explicit. So we're just using functions and pointers to model what's really happening in C++ when you're using classes. All right? So here's a function that's supposed to be a constructor for a counter class. It takes the pointer to the object and a starting value. Here's an increment method, but it's really just a function. It takes a pointer to the counter you'd like to modify and increment its count. Okay? Reset takes a pointer to the object you'd like to modify. gives it a new value. I guess this could be called some other value, starting value, new value, something like that, but that's fine. And then finally, retrieve the counter's count. You give it a pointer to yourself. It's supposed to be a const method, so I'll make it a const pointer. Why not? And you give back the count that's stored inside of your struct that you're pointing to. Okay? This will make a lot more sense when you get into it and look at the comments. But here's the idea. For example, when somebody's calling counter inc, somebody's giving you a pointer to the counter object that you want to increment inside of this self parameter. So self points to a counter object which holds a count. You need to implement it this way so that that object now holds the count 43 after that inc function has finished. Does that make sense? You're essentially creating classes from scratch. You're going through pointers, and so that's just more experience with using pointers. You'll have to use maybe the arrow operator, if you remember that, because there's a struct at the other end. But yeah, that's pretty much what you'll be implementing. Follow the comments, and it shouldn't be too bad. And here's the CPP file. It's just nothing super long. Just implement all those functions, which are supposed to be methods, right there. And then I have a test file. So here's how it would work. Here's how it's going to do it. So, for example, the inc test. So I make a counter on the heap, because why not? And I construct it. So I call the constructor. I call inc on that C object. It's a pointer to a counter, right? And then I make sure that after constructing and inking 3 times, the count inside should be 3, right? That's what your methods should have done to the counter object. Does that make sense? So that's what the tests are doing. They're just making sure that those functions that are acting as methods are doing the right thing. This one tests reset, this one tests get count, all that fun stuff, right? And then once you've got everything working, you need to add 2 tests of your own to the end here, just like you've been doing. So add 2 more tests in this style and test whatever you like, and that will be the end of it. All right, so you will be creating classes just like C++ is doing for you secretly under the hood, just using structs and functions that take a pointer to an object. All right, and then finally you'll be making tests. So any questions about any of that? So you're manipulating 3 files, the implementation for rotate 3, the counter library implementation file, and then the test file. You'll be adding some tests. Okay, so those are the 3 files that you turn in. Notice that you're not touching any of the header files, so you're not allowed to change those. You're not turning them in, so you're not allowed to touch them. All right, so yeah, that's lab 7. And that is all that I wanted to say, I think.